we had done some kind of case analysis to understand this Barkasian criterion just before. So now we will move on. Now we will see the working principle of practical oscillator. So oscillators do not have any input signal. It works without input signal because it has naturally thermal noise that will act as an input. So now I am saying something different from what I said in the previous slide. So here I said we are applying the input signal and we are getting output, and then we are feeding back, and then we are combining and we are applying back to the amplifier, right? But in this slide, I say oscillators do not have any input signal. Actually, this is the truth. Oscillators do not have any input signal. So we do not apply any input signal, but oscillator can still produce oscillations at the output. How? Because whenever these stages are processing the signal, it has, of course, you have to give the power supply, right? If this is the operational amplifier, then you have to give this VSAT plus VSAT and minus VSAT. That is kind of power supply. This is not the input signal. Remember, that's different. This is the input signal. And this is just the biasing voltages. So whenever this amplifier powered up, there is a thermal noise naturally generated by these devices. So because of this closed loop amplification, this thermal noise will get more and more amplified, and it will give enough oscillations at the output. We will see here now. So why I mentioned about V in here? Because of this mathematical analysis, we must assume the V in here. So that is why here I had given in this first slide, V out is equal to A times V in. Here, A times V in, and the VF is equal to beta times V out. That is the VF. And then we have created some kind of equations 1, 2, 3, and then we did some case analysis to analyze this Barkasian criterion. But practically, we do not apply any input to this oscillator. That is what mentioned here. Oscillators do not have any input signal, but because it has already thermal noise, we are using this thermal noise as an input and amplifying this and feeding back again and again. So it will be used, it will act as an input. So even though V in is equal to 0, oscillators can generate oscillations because of thermal noise. Okay, so initially we make A beta is greater than 1. This will help to build a thermal noise over time. So initially we make this loop gain is greater than 1 until we develop the thermal noise to certain level. After it reaches this thermal noise reaches to certain level, we make this A beta is equal to 1. That is the Barkasian criterion. So that's what mentioned here. Once the required amplitude is achieved in thermal noise, A beta becomes 1. Then it becomes a sustained oscillation. So this is the oscillator output. So we do not have any input to the oscillator. So initially the oscillator will start from 0, little by little. The thermal noise will be very little. And then when it feeds to the feedback loop, it will become more and more bigger. So after it reach the required amplitude, then we immediately change this A beta value is equal to unity. Then it will maintain this amplitude at the output. So just remember, there is no input signal to the oscillator, and so just a thermal noise, it acts as an input. So after it becomes certain value, then we can maintain that, and the oscillator will produce sustained oscillations. So again, now we can see one more mathematical derivation, that is output V naught is equal to A times V in plus VF here. So I just rewrite the output equation little bit differently now. So V naught is equal to A times VF plus V in. So we are adding this VF plus V in and applying here. So A is here. So A times VF plus V in. But we already know VF is equal to beta times V naught, right? So V naught we are applying here. So beta. So this is VF. So this is the VF. This is the equation number 2 from the previous slide. So now V naught is equal to A times. We apply this VF value in this equation. So V in plus beta V naught, right? So we are just applying this. And now we are multiplying this inside. So A times V in plus A times beta V naught. So now A beta V naught, we are taking this to the left side because we want output. So V naught minus A beta V naught is equal to A times V in. So V naught, you can take it as a common. Then it will be minus 1 minus A beta is equal to A times V in. So oscillators, we know V in is equal to 0. So if you apply the 0 value here, then this equation will become like this. V naught 1 minus A beta is equal to 0. And then V naught, if you bring this side, it will become 0. So 1 minus A beta is equal to 0. Finally, we will get like this. This equation will become like this if you apply this condition. So 1 minus A beta is equal to 0. So we can rewrite this equation. So A beta is equal to 1. So minus A beta minus 1. So minus minus we can cancel. So A beta is equal to 1. So this is Barkhausen criterion. So if I ask you to prove the Barkhausen criterion for the oscillator circuit, this is the derivation you have to do. So you are just getting the output, and then we are just replacing this VF value, and then it's very simple and straightforward derivation. Finally, it will give you A beta is equal to 1. Remember, Barkhausen criteria is giving us two conditions. This is the first condition. Overall loop gain must be equal to 1 in order to get sustained oscillation or the constant value at the output of the oscillator. So here what we had seen was what is oscillation and what is oscillator, and what are the conditions of Barkhausen criterion. So Barkhausen criterion, and mathematically we have proved the Barkhausen criterion by creating or generating the equations and applying the conditions, and we got this A beta equal to 1. But before that, we had done some kind of case analysis. The case analysis, we have applied A beta is equal greater than 1, and we have applied A beta is less than 1, and we have applied A beta is equal to 1. And we had also given some numerical example. So for example, greater than 1, I used 1.1 volt, less than 1, I used 0.99 volt, and equal to 1. And we found that whenever the A beta is greater than or less than 1, the oscillation is not stable. Either it will increase or either it will die. It will be like this and then it will go down. But whenever A beta is equal to 1, then the oscillation is not dying or getting more and more increase, it's stable. So we did the case analysis, and then based on the case analysis, we have also derived this Barkhausen criterion mathematically. So just try to remember this. I want you to remember mainly the two conditions of this Barkhausen criterion and how to reach or achieve this A beta is equal to 1. Remember, whenever we do this kind of circuit analysis, we need to make some kind of assumption in order to derive the formulas. because the formula, whatever we derive, this is the most common and general one. You can apply in any kind of oscillators, the same conditions. In any kind of oscillator, like we are going to see so many different types of oscillators later. So in each oscillator, you are going to use different components to design the circuit, but regardless, it must follow these conditions. So then only we can get the standard or constant value at the output. Otherwise, the oscillation will die or it will keep increase indefinitely. So I think now it's 12 o'clock. So we will stop here because I'm going to start the new topic next week, since we do not have enough time to cover RC phase shift oscillators. So next week we will see all the major types of oscillators, which are RC phase shift oscillators and Wien bridge oscillators, crystal and Hartley and Colpitts oscillators. So we will see how can we construct a circuit, how can we produce oscillations by using these circuits. So far, if you have questions, just ask me. Okay, thank you for today. So if you have questions, just contact me, or now we will stop here.